Okay, so I want to give the theorem regarding the convergence of Fourier series. So what is the context? So we have a function, f is defined on the interval 0 to L. Okay, this is going to be for the Fourier cosine and sine series. We could also look at the full Fourier series. So f is defined on the interval 0 to L. The Fourier cosine series for f, I'm going to write this as f of x wiggle the sum, whoops, I forgot the first term, 1/2 a 0 plus the sum k equals 1 to infinity ak cosine k pi over Lx. This is the Fourier cosine series where the ak coefficients are given by 2 over the length of the interval times the integral from 0 to L f of y cosine k pi over Ly dy. That's the Fourier cosine series. And the Fourier sine series, FSS, the Fourier sine series, f of x is going to be equal to the sum k equals 1 to infinity bk sine k pi over Lx. And the bk coefficients are given similarly up here, but with sines instead of cosines. So it's going to be 2 over L times the integral from 0 to L f of y sine k pi over Ly dy. I know it's exhilarating to just hear me read off integrals. It's a little story that I'll tell while I'm finding another black marker. When I was in grad school, I had there was a professor there who, at the time, was married to a lawyer, and the lawyer had some court case or something that she was working on, and wanted the professor for whatever reason needed to have a written transcript of some technical math paper with just tons and tons of formulas everywhere. And so the professor was like, well, I could read it out, but it's not like it's gonna sound completely crazy. And she was like, yeah, that's fine, you can do it. It doesn't matter. Just whatever, we need this just to check some boxes or something. So that's what he did. I don't know why I thought that story was interesting. I guess I'm connecting it to the fact that I was just reading off these integrals. I guess another thing that's interesting about the story is that for whatever reason he wasn't allowed to get paid for this. I don't know why, weird legal stuff. So as a gift, he got like a bottle of scotch or something. Okay. That also is not very interesting. So my apologies for wasting your time. Anyways, all right. So let's look at the theorem on the convergence of this series. And so what we did last time is we started. Let's review what we did last time. We started with a function defined from 0 to L. We computed its sine series and its cosine series from 0 to L, and then we said, okay, well, what prevents us from plugging in, instead of just plugging in a number from 0 to L here and here, there's nothing that prevents us from plugging in other numbers. And we can actually figure out what it's going to look like just from what's happening from 0 to L, because for the cosine functions, we know they're even. So we'll first take the even reflection, we'll take the even extension from minus L to L, and then they're periodic. The cosine functions are periodic, so we're just gonna copy and paste whatever we have. We're just gonna copy and paste that to positive infinity and negative infinity. And for the sine series, it was also similar, except we did the odd extension. And this is essentially what the theorem says about the convergence of Fourier series. So we were only interested ostensibly just from 0 to L, but then we looked at what happens from minus infinity to infinity on the whole real line. And that's actually going to help us doing the odd or even extension and then doing the periodic extension of that. that's actually going to help us determine where and to what a function's Fourier series converges. So let's look at the Fourier cosine series first. So let's see, I think I'm going to write the theorems kind of down here and then illustrate them up here. So for the Fourier cosine series, step one is to sketch. So we're going to sketch. So sketch slash find. Let me say find. Find the even extension. Okay, so f is originally defined on 0 to L. The even extension now makes it defined from minus L to L. 2. So find, we're not really finding, we're just saying we're just defining f from minus L to L as being the even part. Okay, step 2 is to find the periodic extension, the PE of this. Okay, so we're going to take the even extension from minus L to L, then take the periodic extension of this from minus infinity to infinity. That's where we're just copying and pasting the graph. And 3, this is like kind of how we determine to what the Fourier cosine series converges to. The Fourier cosine series will converge to the even E periodic P. Whoops, what am I doing with 4 things on my E? The Fourier cosine series will converge to the even periodic extension where it's continuous, and to the average at a jump. And I'll explain more what this means by way of examples. Okay, so this is the Fourier cosine series. Okay, before I tell you the theorem for the Fourier sine series, let me illustrate what's going to happen with the Fourier cosine series. So let's say, again, I'm initially, let's say, only going to be concerned with functions from 0 to L. I'll make it a little bit longer. I'm only, let's say, initially concerned with functions from 0 to L. And let's say I have a function that looks roughly, let's say my function looks like this. And I'll call this 1. Okay, so maybe it's like x squared over L squared or something. I guess that would give us something that looks like this. But it doesn't matter, the exact formula doesn't matter. This is what the graph looks like from 0 to L. Okay, so the first thing that I'm going to do is I'm going to take the even extension. So I'm just going to reflect it across the y-axis. And I'm going to get something like this. And that means that this right here is minus L. And now I'm going to take the periodic extension. So if this is L, this is 2L, this is 3L, this is L, this is minus 2L, this is minus 3L. So what I'm going to do, I'm just going to take this graph and copy and paste it. So I'm going to have something like this. And then something like this. Okay, so now importantly, we really are just kind of thinking about, we're thinking about the function itself on 0 to L, but we have to be careful about what happens at these points in between, okay? So here, we can just define the function, okay, so what we have done here, I guess what I'm saying is, we've taken the even periodic extension, that's what we have here, and it's continuous everywhere. Okay, now, there's cases where it might not be continuous, but for this function, it's continuous everywhere. Okay, so what this tells us is that the Fourier cosine series will converge to the even periodic extension where the even periodic extension is continuous. And for this function, the even periodic extension is continuous everywhere. So therefore, the Fourier cosine series converges to the even periodic extension everywhere. And in particular, on the interval 0 to L, the Fourier cosine series converges to the function of interest on 0 to L, including 0 and including L. Okay, so if we have something like this, the Fourier cosine series is going to converge exactly to our function at all points from 0 to L. Okay, and you might even be making some observations now. I'll get those, I'll talk about those in just a minute. And if you're not, that's fine. I'm being kind of vague on purpose. Okay, so what about the Fourier sine series? So for the Fourier sine series, the theorem is going to be basically the same, except the theorem is going to be the exact same, except for wherever, instead of using the word even, we're going to use the word odd. But something different will happen with the Fourier sine series in practice that basically guarantees that for most functions we're not going to have convergence at 0 or L, and we'll talk about that in just a minute. Okay, so step one is to find the odd extension. Okay, and since I've already illustrated what's going on with the cosine series, I'm going to kind of do this step by step. So find the odd extension. This is the function that we care about. So the odd extension will be something like this. And this extends down to -1. That's the odd extension. Okay, step 2, find the odd O periodic P extension E of this function. Okay, so the odd periodic extension, okay, so I'm just going to take this and copy and paste it. So from -3L to 2L, it'll look something like this. And then, from -2L to -L is going to follow along the purple line like that. Okay, but now notice here at the points at the L's where the two pieces kind of join, I've got some ambiguity about what's going on. How do I define that if I'm taking the periodic extension? There's two competing values. Okay, so basically right now we're just going to say it's undefined. Now, yeah, so if we're doing the odd periodic extension, we have to say something like this is undefined because there's not enough information to tell us how to define it. And then from -3L to 3L, I take this and I copy and paste it. I'm going to get something that looks roughly like this. And it's going to follow along like that. And of course, for the sine series, I don't know at the L's, at the integer multiples of L, I don't know what it's going to be equal to. Okay, because I'm going to have something coming over from this side as well, and the next branch coming over from that part. Okay, so 3, the Fourier sine series. So I just realized that the C, the cosines are even, and the C is kind of like an even function, and the sine, the S here, is like an odd function. Sorry, that just is an interesting coincidence, because I was writing the S, and then I almost did like this because I was thinking even extension, even though the sign is odd. So it's a little weird thing that happened in my brain that just then. Okay, so the Fourier sine series will converge to the odd periodic extension. The Fourier sine series will converge to the odd periodic extension where it's continuous and to the average at a jump. Okay. So what do I mean by this average thing? Well, okay, where is the periodic extension discontinuous? Well, it's going to be at these odd integer multiples of L. I think I said earlier that there's going to be the circles at integer multiples, but notice that the even integers, both parts are equal to 0 there. So it's only going to be the odd integer multiples where it's discontinuous. So let's look at this one right here. So it's discontinuous here. So where does the sine series converge to? Well, it's going to be to the average. This is a jump discontinuity right here, right? So it's going to converge to the average of the two jumps, the average value of the left-hand limit and the right-hand limit. So we've got 1 here, we've got -1 here. Okay, so things aren't exactly to scale, or scale's not even the right word. They're just okay. -1 there, the function is, so the right-hand limit is -1, the left-hand limit is 1. The average values of those two numbers is 0. And so the sine series converges to 0 there. And similarly, it converges to 0 here and 0 there. Of course, we already know that at these multiples, at the integer multiples of L, we know sine has to be equal to, the sine series has to be equal to 0 because of the sine functions here. If I have an integer multiple of L, then I've got sine of an integer times pi, and so that's always going to be equal to 0. Okay, so I know that at the integer multiples of L, the series has to converge to 0. And that's covered by this case here. What isn't covered by just kind of plugging in integer multiples of L is what happens if we have a discontinuity in the interval from 0 to L. Okay, and that's what we're going to look at in the next video. We're going to look at an example where we have a discontinuity in the middle of the interval from 0 to L and see what the cosine and sine series will look like then. And this is also a question that's very similar to the homework.